Welcome back to this class. Today we will discuss about the weight estimation. We will actually estimate the weight of the aircraft based on our requirement. Okay, and not only will take requirement only to estimate the weight. We also go with the historical data which is already published for the weight estimation of the our aircraft. So now we'll go back to the first slide, and we can write our total weight as a payload weight, structure weight, power plant weight, fuel weight or energy weight, subsystem weight, pilot weight and crew weight. Okay. So now here fuel, that means if you are using fuel type of engine, the fuel is required for a combustion, or if you are using just a, like for example electric motor and all, then you can put energy battery instead of fuel. So choice. Okay. Payload, this is a requirement because if you are designing an unmanned aircraft, then you can carry the camera. Okay, you can carry the warhead. So payload comes under that category. Even for agriculture purpose, you can take some uh, uh, what you shall call fertilizer and all these things to spray. Okay, and this structure weight is nothing but the weight of aircraft wing, weight of tail, weight of fuselage, weight of landing gear, weight of strut, and this is a power plant weight. And if you are using just a conventional aircraft for a single engine or two engine, what will be the weight of that power plant? Associated to this, what will be the weight of the propeller? So engine, propeller, this combined, this weight will be called the power plant weight. And subsystems, and this is pilot weight. And along with pilot, if there is a passenger is sitting, two, if you are designing for a 2 passenger aircraft, 3 passenger aircraft, 4 passenger aircraft, or like 60 passenger aircraft, so depending upon that you can put the weight of the pilot. Okay, all the generally all kind of category will have this kind of weight. Okay, and if you sum up all the weight, you will get the total weight. Okay, and if you are not using if the pilot is not there, if the no crew is there, then it is called the unmanned aircraft. Okay, so this the equation which I will drive, it is valid for both manned aircraft and unmanned aircraft. So already, as I already told that if you are not having any idea about individual weight, so it is better to look the historical data in order to get the ratio and plug into this equation and finally obtain the total weight of the aircraft. Okay, so now you divide by W, what you can get, W payload plus W pilot divided by W naught, and this divided by W naught, this part W naught divided by all the part is divided by the W naught. Okay, now this W structure by W naught is structure weight ratio. Okay, for example, like if any unmanned aircraft is sized or any manned aircraft size. So if it is like that, for example, 100 of 20 to 200 aircraft has been sized, so you can look it into that data and you can get an idea what kind of structure weight ratio for a our case. Okay, now similarly for a power plant and similarly for a fuel and as well as a subsystem. Okay, now so if you rearrange this equation, you will get the W naught expression. Okay, now you can find out this W structure by W naught from literature review, and this is a power plant weight ratio, power plant weight fraction also from literature review, subsystem also from literature review, and W fuel by W naught, that comes from the requirement. Okay, and now what kind of payload, it is fixed, and if it is a manned aircraft, there will be the pilot weight and crew weight. Okay, so we can go with we'll have a little bit feel on the past historical data. So what we can look first, as I told, the what is the empty mass fraction. So empty mass is the mass, total mass of the aircraft when you exclude the fuel weight and crew weight, okay, and as well as the payload weight. So you can see that different kind of aircraft is listed here, and these are the total mass, and this is the empty mass, and this is the ratio. So you can see that this kind of a coverage, it is around 0.23 percentage, and when what aircraft you will pick, see the famous aircraft Boeing 777-300, the ratio is around 0.52, and you will beach jet, if you consider, this is like 0.66, and uh, and one more thing, this is global hug, you can, if you consider, this is a 0.37. So you can see that the empty weight fraction is around 0.5, 0.6. So depending upon your category of aircraft, you can actually look at this historical data, and you can at least take the rough value in order to estimate our total aircraft. Okay. Now this is in fighter case, you will having a 0.67, little more than the 0.6. We'll go back to this. So now empty weight has been done, and then you have a kind of some feeling for other weight fraction also. For example, like a fuel weight. Okay, although we will estimate the fuel weight based on our requirement, but kindly look at into this. Okay, again, so many aircraft has been listed here, so you can see the fuel weight here is, for example, what you Boeing 777 is around 41 percentage. Okay, and you can consider some another aircraft, F-16 fighter aircraft, you will have a 0.16. Okay, and for Airbus also 0.41. So you can see that Boeing and Airbus is similar, right? Okay, so you can see the and one the typical value is around 0.3, 0.4. The depending upon the category to category aircraft, this value is changing. So again, you can take some idea when you calculate the fuel weight fraction from the requirement. Then you have an idea whether you are going in a right direction or wrong direction based on historical data. Okay. Again, if I go back to this another weight, you can, this is a crew also. You can have some crew weight idea also. Crew weight. Okay, this is the first one. Now you can see that this is a hang glider, kite, paraglider. It has a 70 to 80% of the total takeoff weight. Okay, so most of the weight is crew only, 70 to 80%. Remaining is the structure part. And when you go from 1 to 2, like from a single seater glider airplane, how this dropped, only you can take a 10 to 20%. Okay, for twin seat motor glider, 10 to 30%. Okay, ultralight 30 to 50%. So you have a, and see, very surprising, in fighter 0.2 to 0.4. That means your crew weight is very less than compared to the total weight of the fighter aircraft. So in fighter aircraft, it is less than 1. Okay, so most of the weight is going in a fuel, structures, power plant, subsystem, payload, and less weight in a crew side. Okay, so I think you have a idea about to estimate the weight of the aircraft. Okay, so as I said, fuel weight comes from the requirement. Okay, and the requirement can be, for example, you are starting from 0 point, which is takeoff starting point, and this is 1, which is the ending of the ending of takeoff, and you will rotate here. Okay, and then you will climb. Okay, and then you will attain some altitude and you will cruise, and if there is a requirement, you will loiter. Okay, again cruise. Okay, and then you may descend. Okay, and then finally you may land. Okay, so you can mark as a 0.1, this is 2, this is 3, this is 4, this is 5, and this is 6. Okay, it is not always you will follow this kind of trend. Okay, you may go from takeoff and then climb and then cruise and then loiter and then go again, return back to the base. This kind of profile you can, flight profile you can follow. Or you can, if you have, if you are like for example current aircraft VTOL air taxi, okay, then you can directly take off from this place and attain some height and cruise, okay, and land some, right, and in meanwhile you can loiter also and you can return to the same place also. So there is so many profile. Based on that you can estimate the total aircraft fuel weight fraction. But here let's say I am listing my requirement as a, I want to go from one place to another place, that's it. Okay, let's say for example, first example we will consider here, we want to design our some kind of air taxi, okay, which we used to take from one place to the another place. Okay, okay. For example, like I will start from Kashmir and then I will go to Kanyakumari. That is our ultimate aim. Okay, and in later class we will take some another example for unmanned aircraft, because this course is all about manned aircraft as well as unmanned aircraft. So we will take one example for manned and one example for unmanned aircraft. Okay, the requirement of the range, if it is given, then you can use R equal to eta PR by C L by D ln W naught by W1. Okay, and you can estimate the what is our weight fuel weight fraction. Okay, so can you tell me what was the range we have taken? 4,000, no? So R is 4,000 kilometer. Okay, now if I put 4,000 here, and now in the preliminary stage I am taking a propulsion efficiency 0.6, okay, to be more conservative side. If your propeller is variable pitch efficient propeller, and then you may reach to the 0.8 also the efficiency, and L by D I am taking 10. So now an specific fuel consumption I am taking 0.2 kg per kilowatt hour. Now I will give some feel for this L by D things and specific fuel consumption, since we have discussed here. So now this is a maximum aerodynamic efficiency L by D max, here it is listed. Sail plane 20 to 35. See, whatever I am telling to you L by D specific fuel consumption in detail we will study in the aircraft performance part in this course later. Okay, now see this, in jet transport it is 12 to 20 and general aviation 10 to 15. Okay, like that, and helicopter is 2 to 4. Okay, so you can see that in sail plane it is more, because your span is more, right? So induced drag factor will be less, so lift will be more than compared to the drag, so L by D will be more. We will discuss in detail in the later part of this course when I will teach you the airplane performance. Okay, so it is fair enough to take 10, right? Perfect, right? Fair enough. Oh, okay, I have taken 10. Okay, you can see that there is a turbojet 0.9 and this is listed in British unit lb hour per lb. So 0.9, 0.7, 0.4, 0.5 to 0.8 for a turboprop, and piston is 0.4, because see in turbojet it is 0.9 and piston is 0.4. So turbojet is taking is twice rise specific fuel consumption. Okay, so this will take more fuel. It will consume more fuel to produce unit thrust per unit time, and this will be almost half of the turbojet. Okay, so this kind of take some historical data, and if you're taking any value it should make sense, right? Why I am taking this value. Okay, so when I am taking C equal to 0.2 kg, I have converted this unit into kg per kilowatt hour. Okay, you can go back to that slide, take the value and convert, you will get the same. So now if you substitute all the value which have taken, you will get W naught by W1 is 1.4380, and you reverse this, you will get W1 by W naught equal to 0.6954. You subtract the one from both the side, you will get 0.3046, and W naught minus W1 will be your fuel weight, because your starting weight was W naught and your end weight was W1. So W naught minus W1 will be the fuel weight consumed. Okay. If you divide by W naught, you will get WF by W naught, and it will will be ending to 0.3046. So now approximately 0.31, that means 31% you are getting here, and you have some feel for this fuel weight. Okay, so here is the ratio of fuel. Okay, you can see that whatever so far we have calculated, it is belonging into that this Platus PC12 and also Beach Super King Air. Okay, perfect. So whatever you will calculate, you should also have a feel for that. Okay, now if you substitute this 0.3046 value in this expression which we have derived here, you will get the total takeoff weight. So now from the historical data, we will take W structure by W naught as a 30%. It is a very conservative number. That means if you go beyond that 30% or 35%, it is not recommended. So structure weight, generally maximum weight is around 30% only. So to be more conservative, we have taken W structure by W naught. Okay, and in last slide I have given you the reference also. You can go to the reference and you can collect the ratio of this. Okay, and then power plant I have taken 15%, and fuel weight already we have got from the requirement, and subsystem weight it is 10%. So 30, 15 and 10 will be the 55. So 55% will be the empty weight fraction, and you will see in many aircraft the empty weight fraction is around 0.6, 0.7, 0.5. You can go back, you can check uh, empty weight fraction here. Empty weight fraction in our case it is coming 0.5. So in which case you will belong, it is Cessna 750. Okay, 55 we are getting. Okay, so many empty weight fraction is listed here. Okay, you can see that in fighter aircraft also there is a 67% empty weight fraction. That means the part which is taken care by the payload, fuel and crew will be less than compared to the all other weight, power plant weight, structure weight. Okay, and okay, if you substitute this value, and I am taking 20 kg as a payload, that can be camera weight and all, and one pilot and one crew, so total weight is 80 pilot weight, 80 crew weight, 80 160, and 20 is a payload weight. So in numerator you will be having a 180 kg, and 1 minus empty weight fraction will be 0.55, and here you will be having approximately 0.31, and if you calculate, you will get the total weight is coming around 1238 kg. So this is the total weight, and in next class we will size the wing in order to lift the weight which we got in today class. Thank you so much.